That is funny.
I can't light it. I think that's why those lights are. Yeah.
That's why it's good to go camping once in a while. And I mean real camping, not like camping with modern commodities.
So I shouldn't just bring my whole RV through your house.
Your RV that has no big screen TV inside because the screen is outside, right? You have a projector,
Yeah,
and then your
I
entire
have
RV
outside.
becomes a screen.
Yeah, I'm getting some real outside time. getting in touch with nature.
Well, I'll tell you one thing about camping, and sometimes an RV is required, especially if you go to Bodega Bay. Has anyone ever tried to do tent camping in Bodega Bay, otherwise known as Blodega Bay? I tried to set up tent once, and my friend, also tried to set up tent once, and he and I are both, pretty good at setting up tents because we have done it like many, many years. And both of our tents broke because of the wind. Because of the wind, yeah. So we had to basically put all the stuff out of the minivans and then sleep inside the minivan. But because my minivan, doesn't have that much space for like 4 people to sleep in, so fortunately we had enough tarp. So we put a tarp over the seats that we removed from the minivan, and then I found that under the tarp it was actually pretty dry. So I was sleeping under the tarp on the ground, when it was like raining and howling outside. And I stayed like that for about 4 or 5 days. When we left, I found that I had two buddies inside under the tarp. There was one cricket on one side and one millipede on the other side. Yeah, millipedes don't bother me. I mean, some people think they're really gross, but millipedes are vegetarian. They only need compost, so they're composters. They're good. They're good for the environment. And crickets, man, they're edible. You just have to prepare them right. Yep, midnight snack.
Have you ever tried camping with a hammock?
Nope,
No?
that doesn't sound very comfortable.
It's not bad.
It's not bad. Okay, all right. So this is the proof that I worked on Monday, and then I worked up to the last step and go like, I don't know how to get from here. So I found out that I know how to get from here. Okay, so here's the last portion of this particular proof. So when we get here, what we need to do is to transition so that we re-express the top. Instead of expressing it as the cardinality of V plus 1, I will re-express it as the cardinality of V union with the element of E. But we know E is not in V, so that's why it is the same as the cardinality of V plus 1. So I'm rewriting it like that, okay? And then don't forget the factorial. And then with the denominator, we're going to do the same thing. So we have V union with E, the whole thing. But then you will go like, but this is like the cardinality of V plus 1. This entire thing is this thing plus 1. So that's not going to be the same thing as the cardinality of V minus J. So what we need to do is to say, well, let's subtract J plus 1 from it. Then it's the same, right? The whole thing factorial. Is that okay? Does that make sense? So this is actually what we needed, because what we want to do is to convert this back into permutations. So now when you look at this, it fits into the definition of permutations, where the number of items that we are choosing from is the cardinality of V union with the set of E. And out of that many, we are choosing J plus 1. So if you look up the definition of permutation, these two are equivalent. It's just another way to express the same thing. And this is the end of the proof, because the theorem was exactly asking about the cardinality of omega J plus 1 with V union with E as the set of the choices. And now we can relate it to the permutation of the cardinality of V union with E, choosing J plus 1. And that's exactly what we wanted, because if you go back a little bit up, into the question itself. Okay, let me see if I can. Yep, there we go. Go up a little bit more. And the theorem, okay, let me switch to a highlighter here. So the theorem is this part here. That part is the theorem, and you can see how our proof exactly matches what the theorem is stating, except it is an induction step. Yep. Oh, now that it's highlighted, you cannot read it. There we go. So the highlighter doesn't have enough transparency. So are we good so far? Yep. Okay, so that pretty much completes the entire proof. So I was actually correct working up to the last step on Monday. I just didn't relate it back to the theorem that we were proving. So that was the only addition to this particular proof. So are we okay with this proof so far? Okay. So yes, I understand this proof is a little bit too much, for an exam question. The problem is, over the years, I have already used a lot of questions, and since I tend not to reuse questions from the past, so that means the number of choices I have left is getting smaller and smaller. And sometimes I look at the material that we have been talking about, and I try to combine things, and this is kind of the combination of a few things. So is that okay? I mean, once I explain it, was the explanation okay? Does everybody understand the explanation? Okay, very good. Yep. Like that? Yep. I actually recorded a separate clip on Monday or yesterday, I cannot remember which day, as an extension of the class recording, so you can actually watch that too. Explains exactly the same thing. So are we good? All right, cool. So we get back to big O, little o, omega, and theta discussion now. So let me just pop this up and see if there are any questions, because we are pretty much done with this particular slide. And the bottom line is, we want a tight bound if it is possible. So the tight bound definition is if f of n is an element of theta, that means this is true if and only if f of n is an element of big O, and f of n is also an element of big omega. Big O is the upper bound, big omega is the lower bound. So if g of n is the upper bound and also the lower bound of f of n, then it is known as a tight bound, which is typically the ideal case. If we can find the theta of a particular time complexity, that will be best. Sometimes it is not possible, okay, because sometimes with certain algorithms, the best case and the worst case are very different. So we can only say, well, in the best case, this is the lower bound, but in the worst case, this is the upper bound, and they are not the same. So are we good so far with the terminology? Okay. So if we're okay with this terminology, we move ahead to recursive definitions and algorithms. This slide is, if you guys have read it already, because you're supposed to read ahead of me by about a module, this is a pretty light treatment of recursive algorithms. So we'll go ahead and just kind of quickly go through this. Maybe we'll use the entire day today to go through this. Maybe we'll have some more time left to do something else. So the first example is a very typical example to explain what is recursion, and that's factorial. Okay, we are very familiar with factorial at this point because of the discussion of permutations, combinations, counting, and all kinds of stuff like that. So the way we define factorial is if n is greater than or equal to 1, then factorial is defined to be n factorial is defined as n times n minus 1 factorial. Okay, that's one way to define factorial. But you have to have a base case, right? You know, the recursion has to end at some point. So we define 0 factorial to be 1. And once we have the recursive definition, which is n factorial equals to n times n minus 1, the whole thing factorial, and then we have the end of the recursion, which is 0 factorial is 1, then we can use this as an example, okay? This is just an example. We started with 4 factorial. Then we ask, does 4 equal to 0? Nope. Okay. Then it becomes 4 times 3 factorial using the recursive rule. And then we have 3 times 2 factorial, 2 times 1 factorial, 1 times 0 factorial. At that point, 0 factorial is by definition 1. So we put that 1 back into here. Then we can resolve 1 times 1 to be 1, 2 times 1 to be 2, 3 times 2 to be 6, and then 4 times 6 to be 24. So that's, generally speaking, is how recursion works when you use subroutines and stuff like that. Then I use GNU as a joke, okay? Because in computer science there are many definitions that are infinitely recursive. Did I talk about lame and wine? I think I thought it. No, I did not. Okay, I must have mentioned it in another class then. Okay, so in computer science there are many definitions that are jokingly recursive. Okay, so there's lame, okay, which is an MP3 encoder. But when you look up the name of lame, L-A-M-E, okay, let me see, where's the name? Nope. So it only explains that lame is a high quality MPEG audio layer 3 MP3 encoder. But when you look up the name of why they chose that name, it's not explained here. It has to be explained somewhere. Huh? Yeah, Wikipedia definitely has it. There we go. There we go. So it says right here, lame is a recursive acronym for lame, ain't, and MP3 encoder, which it is. The reason why they say that lame, ain't, and MP3 encoder, this is back in the days when MP3 was a patented algorithm. So anyone who implements the MP3 decoding algorithm or encoding algorithm without getting a not copyright, but without a permission from the author is an infringement on the patent and potentially can be sued. So that's why, lame has to make this declaration that lame ain't an MP3 encoder, which it was and still is. Okay? So this is one. And then for those of you who use Linux and still want to play games that run in Windows, you're probably familiar with Wine. So Wine, most people think that it is Windows emulator. That is not the case. Wine is not an emulator, which it is. So you can see how in computer science, recursion or the concept of a recursive definition is pretty, common, because most computer scientists, are, they like to joke around, and recursive definitions is one way that they joke around. And then the other one obviously is GNU. So GNU is not Unix. But what exactly is GNU? GNU is not Unix. So all you can confirm is GNU is not Unix, but you can never really quite figure out what GNU really represents. So that's kind of the idea. All right, so that is done. So now we work with the actual C code of factorial, which most of you should know already by now. Okay, so this is one way to do it. I know some people can simplify this quite a bit, but the idea is it's pretty simple. Okay. And for those of you who do not like to use ternary operators, there's a way to do it using a ternary operator. So you can say int f, okay, int n, and then you just have a single return statement because we are using a ternary expression here. So the ternary expression just has to say if n is greater than 0, then the result is n times the factorial of n minus 1. Otherwise, you return a 1 because n is less than, quote unquote, less than or equal to 0. And that's it. And you can see how a ternary expression is very powerful because the full algorithm or the full C program subroutine on the left-hand side is now condensed to a single line. Okay, so there are reasons why some people, including myself, prefer to use the ternary expression whenever it is appropriate. Like in this case, I think it is appropriate. It really expresses the same kind of logic, but using much more concise logic. So are we good so far with factorial? Okay. So the next thing is Pascal's triangle. So this is one way to compute Pascal's triangle, where R represents the row and then C represents the column on the row. Okay. But what we know about Pascal's triangle is, it's really about combination, right? So we are really computing, what is the quantity of choosing C from R. Is that okay? So if you look at Pascal, the name Pascal or the subroutine name Pascal as combination, what is this reminding you of? It's a particular theorem that we have talked about in this class. No, it's a theorem that we used in order to prove the binomial theorem. Yep, but what is the name of that theorem? It's called Pascal's identity. Very good. Good job. Yes, Pascal's identity. So this really is, Pascal's identity, but encoded into a subroutine. That's all. Is that okay? But just like the factorial program, this one can also be done using a ternary expression. Okay? This is the condition that we are evaluating. This is the then value, which is a 1. This is the else value. Because the whole thing is nothing more than a if, then, else. Okay? With one of the branches being recursive, being this one here. Now, the only difference between this one and the factorial program is this one has got 2 recursive calls instead of just one recursive call. When you're dealing with a subroutine and it only has one recursive call and it can be done as quote unquote the last thing, you can easily turn it into just a loop. Okay, it's called tail end recursion. But when you have multiple recursion points like this one, then it's not so easy to convert it mechanically into a loop. Now, obviously there are ways to do this without having to do a lot of recursive calls, but it is not going to be as simple as turning it into a simple loop. So are we okay so far with this implementation? Yes? Okay. Just so that we are clear, okay, I'm going to go back to the discrete probability module so that I can mention, where we have encountered this. Because I want to make sure that you guys can relate the algorithm to the theoretical side of Pascal's identity. Oh, may not be this one then. Huh? Okay. So it's discrete probability then. Let's take a look at this. Yep. So when you look up Pascal's identity, okay, I have to fit the whole thing into one page. Okay, it's not easy. But if you look up this one here, and you look up this thing here, you can see how n plus 1 is how many things we're choosing from. And then when you switch to the algorithm that we were just talking about, okay, which is here, you can see how both recursive calls now specify that we are choosing from r minus 1. So I'm hoping you guys can see the parallel between Pascal's identity and this particular way to find out a particular value in Pascal's triangle. Are we good so far? Okay. So the next one is Tower of Hanoi, okay, which is a very fun problem to solve. Okay, it's a fun problem to think about too. Okay, so I'll describe the problem. So the problem is we have 3 poles, and we can label these poles, 1, 2, and 3. Okay, there are many ways to label them. We start with a sorted stack of disks on pole 1, with the largest one at the bottom and the smallest one at the top. So the rule that you have to follow is you cannot put a bigger plate on top of a smaller plate. Okay, that can never happen. And you can only move 1 plate at a time. You cannot just take the entire stack of disks and go like, done. Okay. So you can only move 1 disk at a time, and you can never put a bigger disk on top of a smaller disk. Now, can we put a really small disk on top of a really big disk? Yeah, that's okay. As long as the disk on top is smaller than the disk under it, it's okay. Okay, so the question is, with all of these rules, how do we move a stack of disks from pole 1 to pole 3? Okay, that's the question. So the way we implement this is we first, so the first thing we do is we set up the prototype of the function. So the prototype of the function has all of these parameters, and is basically saying how many disks we are concerned about. Okay, now it doesn't say how many disks there are in total. It only says, how many disks are we concerned about? Is this particular invocation concerned about? Okay, and then from is one of those 3 numbers, can be 1, 2, or 3. 2 is one of the other numbers, and then via is one of those numbers too. But they cannot be the same, obviously. Okay, so you can have from being 1, 2 being 3, and then via being 2, and then you can also have from being 3, 2 being 2, and then via being 1, and so on. So the way you assign the values 1, 2, 3 to from, to, and via is entirely up to you. Okay, as long as you observe those rules of not putting a larger disk on top of a smaller one. So now we look at the base case. Okay, the base case, which means okay, when do we stop recursion? In other words, if you give me this problem, I know how to solve it without any recursion. It's one single step. Okay, well, when n equals to 1, I think we know how to do it. In other words, you are told to move only 1 disk from the from pole to the to pole, and you're told that, well, if you need to, you can use the via pole. So in this case, all you have to do is to say, I'm going to move 1 disk from the from pole, which is going to be into here, to the to pole, which is going to be the %d over here. How many people know how to read printf? Should. Okay, very good. So the %d are placeholders, and then the value that go into the placeholders are the arguments that is after the string. Okay, it's basically the way we do things before C in and C out, before streams in C++. Oh, those are spaces. It's just the way I format it so that a space within quarter string is kind of really stands out, so we know those are just spaces. Okay, so are we good so far from the perspective of the algorithm? We know when we can just perform 1 single step without recursion. We good? Okay. So now the next question is, what if we have to move more than 1 disks? So there's a whole explanation here, okay, of what happens when you have more than 1 disks. So the best way to look at this is to kind of visualize it, okay? So let me see if I can visualize this using, we'll start a new document so I don't mess up this one. So we'll save this and then export it too. So we'll export it to PDF. So now we end up with an extension of pdf.pdf.pdf. because each time I export it, it wants to append an additional PDF to the original file name. Huh? It is like recursion. Okay, we want to zoom in to fit page width. Okay, there we go. So I want to give you this picture, and we got 3 poles, like that. Okay. Oops, wrong color. We want to go back to this color here. Okay, so we got the first pole, we got the second pole, and then we got the last pole. How come there's some transparency in here? I might have accidentally changed the transparency. Oh, I'm still using a highlighter? Oh, that's right. Okay. I'm using a black highlighter. Golf. Okay, so we're going to put some disks here. Okay, so we have, let's say 1 disk here, and a whole bunch of little disks, smaller disks on top. Okay. Okay, so let's say this is my original configuration. And this is pole 1, this is pole 2, and this is pole 3. So the question is, how do I do this? So the key to solve the key of solving this problem is to say, is try to be lazy. Okay, is try to be lazy. Break the big problem into a smaller problem of the same nature. Okay, so what do I mean by that? You basically, now you use a group function, like any good drawing program. There's a group function, right? So I'm going to use a different color this time for sure, because I need to treat the entire group as one thing. So you group this entire thing and say, well, in order to move this whole thing, to pole 3, why don't I move that, the green part, the Christmas tree part, to pole 2, okay? And then I move the largest disk to pole 3, then I can move the Christmas tree back on top of that big plate. Is that okay? All right. So the idea is to do this. First step, okay, I'm going to use red this time. So the first step is to move the Christmas tree so that the Christmas tree is now on the second pole. And then we move the largest disk to the last pole, which is where the destination is supposed to be. And then the third step is to move the Christmas tree from pole 2 to the last, to its final destination, which is here. Okay, I know my picture is not very good, but I hope the idea is okay. So does everybody get the idea? Okay. Then you ask the question, it's like, but Tech, how do you move those 5 disks from pole 1 to pole 2? Well, it has the same nature, as the same kind of feel as the original problem, right? With one exception. Because when you want to move all the disks within the green portion from pole 1 to pole 2, then you have to use pole 3 as your via. That becomes your temporary pole. Is that okay? So once this part is done, then the last disk can be transferred directly from pole 1 to pole 3. Is that okay? And all this time, I still play by the rule of I'm not going to put a larger plate on top of a smaller plate, because every plate inside the green portion, they're all smaller than the largest plate that's at the bottom. Is that okay? So I keep doing stuff like this until it is done. But the step of recursion is simple. So when you look at the entire algorithm, now obviously this is not going to actually move anything. All it's going to do is to say, I'm moving a disk from here to here, I'm moving a disk from here to here, I'm moving a disk from here to here. That's all the output you're going to see from this particular program or from this particular subroutine. But when you look at this part here, I'm moving the n-1 is representing all the disks within the green portion. Okay, so I'm moving those from the from pole to the via pole from my perspective, using the to pole as a via. Okay, so that eventually moves all the stuff in the green triangle to pole 2 from the original problem's perspective. Okay, the second line is moving the one remaining disk, the largest one, from pole 1, which is the from pole, and I'm moving it to the to pole, okay, which is pole 3, and I'm just kind of saying, oh, if you need to, you can use pole 2 as a via, but I don't need to do that because n equals to 1, it is not going to do any further recursion. And then the last step, okay, once I have the largest disk on pole 3, now I can say, oh, move those n minus 1 disks from the via pole, which is pole 2, to the to pole, which is pole 3, but this time I can use pole 1 as the via. Is that okay? And that's it. Looks really simple. So now the question is, how long would it take to solve this problem? Okay? So what do you think? How long do you think it's going to take to solve this problem? It's going to be a long time. So when we say a long time, what kind of, can we approximate that function? What is the upper bound? What is the lower bound? And do we have a tight bound in this case? So we'll talk about that later. We'll handle the time complexity stuff later. But I can already tell you the time complexity of this is n to the power 2 to the power of n, sorry. So it's n to the power of 2. No, the other way around. 2 to the power of n. So if you have 6 disks, it will be taking 64 moves. Yep. Minus 1, I think.
Is that just because, like, at every level of the recursion, you have to go once for n minus 1 and then another recursion for n minus 1 down?
Yep. You can actually look at it from a tree perspective as well. So basically, you look at this as a tree. This becomes a subtree. This becomes a subtree. So the subtree, now the question is, each subtree has also 2 subtrees. So you have a fan out of 2 per node in this tree. And as a result, the total number of nodes that you have, and that's basically, the time complexity approximation, has to do with 2 to the power of the number of levels, which is now limited only by n, because each level you can only reduce n by 1. Yes? Nope. Fibonacci can be made a lot faster than the recursive version. Sorry? Yes. Right. Yeah, but not with Tower of Hanoi. Because there's no state to save. If you look at this entire process, there are no 2 states that are actually the same. If you look at the positioning of all the disks on the 3 poles, there are no 2 states being the same, which means you cannot use the approach that you would otherwise be using to solve the Fibonacci problem, and also the Pascal triangle too. The Pascal triangle problem can use exactly the same technique to make it go super fast, because we're repeating the computation of some values over and over and over again. But in this case, we cannot, because the states of the 3 poles, there's no repetition of those states. Okay? Now, it is entertaining to read the original problem of the Tower of Hanoi. Tower of Hanoi. So if you look up the story, so let me see if they have the story here. Iterative version, origins, there we go. So the story is about an Indian temple which contains a large room with 3 time-worn posts in it, surrounded by 64 golden discs. 64. And you might think, oh, we just worked out, 6 discs will take 64 moves, so 64 is not a big deal. No, we are talking about 2 to the power of 64 here. It's a pretty big number. So acting out so Brahmin priests acting out the command of an ancient prophecy have been moving these disks in accordance with the immutable rules of Brahma since that time. The puzzle is therefore known as the Tower of Brahma puzzle. According to legend, when the last move of the puzzle is completed, the world will end. Okay, so let's do some calculation and find out when the world is going to end. I like problems like these. Okay, so I'm going to use a spreadsheet to help us, just so that I can keep track of all the calculations. Okay, all right. So we are talking about 2 to the power of 64 moves. Okay, minus 1 maybe. Okay, I think it's this many minus 1. Fine. So we are talking about 1.8 ish times 10 to the power of 19 moves. So what do you think how much time do you think it would take to move one disk from one pole to another pole? Just give me a time estimate. Let's call that like 2 seconds, 3 seconds, okay? All right, so we'll put a 3 here so we can change that number later if we need to. So now we look at the product of these two. Okay, this is the total number of seconds. Okay, now this is the thing about numbers is a lot of times we look at a number and we don't really quite know the scale of things. Okay, we just look and go, yeah, that's a lot of seconds. But how many seconds is that? I mean, what do we mean by a lot of seconds? Because sometimes people look at the Unix time representation, which is the number of seconds since 1970. Okay, and that's a lot of seconds too, right? So how does that compare to this? It's like, we don't know because they're both large numbers. So instead of just looking at a number and try to get an idea, we'll just look at, this is number of seconds, right? So now we'll say minutes. So minutes is easy. We just take this number and divide it by 60. Okay, we look at hours then, which is this number divided by 60 again. Then we look at days, which is this number divided by 24. Then we look at years, which is this number, divided by 365.25, okay? Because the number of local Earth rotation around the sun is an irrational number. Now, if you find a planet where its own rotation around the sun is actually an integer, that would be an indication of that planet may actually be created by some intelligent species. I would count it as a very unlikely thing, and it might indicate that the planet is actually a satellite put into orbit by some intelligent species. Especially the case if it takes exactly 42 local rotation to complete one rotation around the sun. 42? Base 10, 42. Okay, so we are looking at years here. Let's look at centuries then. Centuries. Okay, there we go. So we are looking at this number divided by 100. So we're finally getting to the point where we don't need scientific notation anymore. This is the number of centuries, okay? So let's look at this number again. And we say, we kind of estimate the sun is going to expand in what, 4 billion years or something like that? 4 or 5? Okay. So in 4 or 5 billion years, the sun will expand because it's going to run out of fuel. And then it will expand, and the photosphere is going to, and it's going to exceed, or it's going to be at least getting to the Earth's orbit. So we'll be inside the sun, at that point. Okay, and that's 4 billion years, right? 5 billion years or whatever. So, yep. So we say 5 times So a billion is to the power of 10, right? Power of 9, yep. Okay, so this is the number of years that before the sun is going to destroy the earth. And this is the number of, the amount of time before the end of the world according to that particular prophecy. I say we have nothing to worry. In other words, the monks will still be moving the disks while the earth is inside the sun. Huh? That is true. According to our current estimate, yes. So I say we don't have anything to worry about. The temple will probably have to be inside some kind of energy shield so that, it's not so hot that the monks cannot move the discs anymore. So don't you like prophecies like that, where, the time is like, yeah, I don't think we have to worry about that. Huh? There are plenty of animations, actually. If you look up the Tower of Hanoi animations, there are ones where it's programmable. You can specify the number of discs, and you can control the amount of time, the animation sequence itself. Even if you reduce the time, okay, so let's just say that we have robotic monks. So let's say we got robotic monks and they can get things done really fast, like 0.1 seconds between, to move one disk. We still have, let's see, how many zeros do we have here? 3.
That's about 58 billion.
58 billion. Okay, so we are still good, right? That's assuming that we have robotic monks that can move that can move 10 disks per second. That is pretty fast. Well, those are golden disks. Your computer is not going to help. They're actual physical disks. Well, you can kind of know that, if you want this prediction to coincide with the expansion of the sun, we're still 60 times off, right? So that means this has to be 60th of 0.1 in order to meet that deadline. So I'd say those monks have lots of work ahead of them. Better hurry up. All right.
Calculate how many disks it would take for it to coincide at their current rate.
Say that one more time.
So, at their current rate of moving disks, how many disks would it take for it to coincide with the end of the world?
Oh, not a whole lot. So we go back to 3 seconds, right? So we have to find out, how many disks. So you can solve this problem in 2 ways. You can solve it by just reversing the amount of time. And okay, let's do it that way then. Okay, so we say, okay, this is the number of years, right? And then so this time I'm going to do it a little bit faster. Multiply that by 365 and a quarter for days, 24 hours in a day, 16 minutes in an hour, and then 60 seconds in a minute. Okay, so this is the number of seconds that we are talking about. And then we have to divide it by 3. Okay, so we look at this number. We divide it by 3. This is the number of moves that we can make, right? So now we have to use log of 2. Find out what is the power of 2. Yep. We have to add 1 first. Yes. Okay, so we have to add 1 first. So we look at the log, okay, natural log of this number plus 1 divided by the natural log of 2. So we are talking about 55 disks or so.
Not that many less.
Nope, because it's exponential. Yep, it's exponential.
We only have 55 disks left.
I don't think they only have 55 disks left because they only got at the most a few thousands of years to work on this, right?
We only have that much time left, 55 disks.
Yes.
If you measure, the time we have left in disks.
Oh, that would be an interesting way to measure time, right?
We only have 55 disks left, people.
Yep. Yep. So we'll measure our days. Yeah, we'll measure time from now on using disks. So when is this class going to be over? I think about 6 disks or so. When is lunch served? When is dinner served? In about 7 disks. That is funny. I like that. See how cisp440 can be entertaining. Okay, wait, that is not entertaining. Where am I? Recursive definitions. There we go. Okay, so we are. Nope, that is not entertaining. Okay, so we just got to Towers of Hanoi. Okay, the next one is how do you nuke a folder? Deleting a whole directory. Okay, so in most operating system, or the file system to be more exact, of any operating system, a folder cannot be deleted unless it is empty. Okay, that's kind of the rule. So how do you delete a folder? Well, when you don't want to nuke a folder, what you need to do is to say, well, is the folder empty? If the folder is empty, we can now delete it. Okay, what if the folder is not empty? Well, first of all, find all the files and delete the files. But it might have subfolders. So when you encounter a subfolder, then you have to call this subroutine recursively so that that folder is now removed. Then you move on to the next subfolder and so on. So the algorithm to delete a folder would look like this. Okay. If you write your code in C and C++, I think this actually works. Not that I have tested it on my own folders. This is why we have a replicate, right? So we can just test it on a remote server, see if it works. Yep, but these are actual function calls, by the way. I mean, this subroutine actually does compile. So there's an open dir, system call. Unlink is basically delete, and then if the folder is null, that means it is empty, and then you can also change to a folder, chdir, and then you can read dir, which is it kind of gets the job of an iterator, but it's implemented in C, so it's kind of like an iffy way to do iterators. So for each subfolder, you nuke the subfolder, and then you have to go back to the parent folder, and then remove the parent folder, or the current folder, actually. So that's kind of the algorithm to remove a folder. So, but getting back to the point that we're trying to make, this is the recursive point. Okay, it is recursively done. So do we have any questions about all of these examples of recursive calls? Now, this one, how many times do we have to go through nukedir in this loop? It's kind of dependent on how many subfolders you have. Okay, so there's no easy way to tell the number of times that we have to do the recursion. So are we good so far with all of these examples? Okay. So now we look into, let me see, do I have examples like that? Okay. We do not. Okay. Huh? 2 equal signs? This one here? No, it's intentional to be a single equal sign because entry is used here to tell me what is going to be deleted. Yeah, this is the way of an iterator, how an iterator works when you're using just plain C and not using C++. It borrows the concept, but it's not. I can already tell you this is not thread safe. So if you do multi-threading, this is not going to be a good idea. Okay, so let's go ahead and take a look at something that you are very, very familiar with that is non-recursive, okay? How many people know what is string length? strlen, which basically just returns the number of bytes of a C string, which is basically an array of characters that is null terminated, right? Okay, so normally how would you implement a string length, okay? So let's just say that it returns an unsigned, which makes sense, right? And this is string length, and then we have const char pointer. This is my string. So normally, how do you implement this? Okay, unsigned count, initialize that to 0, as long as whatever str is pointing to is non-null, we add 1 to count. And we're done. Okay? Well, I mean, this is one way to do it. There are many other ways to do it too. If you do not like to do counting, there's a different way that is actually faster, slightly faster. So the other way to do this is to use another pointer. So you have another const char, and then you say, old ptr is str, and then you can get rid of this, and then you just return str minus old pointer. Slightly faster. I don't think anyone is going to notice the difference, but yeah, so this is non-recursive. What? So does everybody understand how this works? More or less? No? Okay. So old pointer is basically just saving where the string starts, because I'm going to change that, right? So the second loop here looks really simple, but it's not, because it's using dereference. This is post incrementing and then dereference, which means the dereference is dereferencing str before the increment. So I'm dereferencing it, checking whether it is 0 or not. If it is 0, we get out of the loop. If it is non-zero, we just kind of move on. So it will keep moving on until we get to a null character. So at that point, it will stop. And then we look at str minus o pointer, and it's actually going to be off by 1. So we have to do another minus 1 here. But basically, str will be pointing to 1 byte past the null terminator. So the null terminator is here. It will point 1 byte past that. And then o pointer is still pointing at the very beginning of the entire string. So when you do the subtraction, it will give you the number of items in between the 2 pointers, which is the number of bytes. But we have to do another minus 1 here, because str is going to point to 1 byte past the null terminator because of the post increment. It's an empty body. Yep. The while has nothing to do as the body. In other words, the condition does all the work that we need to do. This is why we like C. Okay, so you look at this and go like, that's not recursive. Aren't we supposed to be talking about recursion this class? Let's turn it into something recursive, right? So we have unsigned strlen, const char str, and now we want to make it recursive. And we also want to use the ternary operator, okay? So we say return, okay? So there's only one statement. So when do you think we got nothing to process? We're done. I can tell you what the answer is. When str points to a null character, right? Because, oh, it's an empty string. I can tell you the length of this string right away. Okay, so we can basically say that and say, yep, that's a 0. Does everybody understand what this means? Why I can use a logical not on star str? Because because a null character is a 0, which is the same thing as a false. So not false is going to be true. So this expression tells me when I should return a value of 0. Okay. So now the question is, what if that is not the case? That means I got at least one character that is not null, right? What about the rest of the string? Yep. Now it is recursive. Huh? Say that one more time.
In this case, would that actually be faster, or is that just for the sake of
Oh, it's going to be way slower. But it is recursive. It has the same order of magnitude. In other words, it has the same time complexity, but it's going to be slower, way slower. Now, the reason why it's going to be way slower, well, you kind of have to take 310 to understand that, because there's a lot of stack operations involved when you're calling and returning and passing parameters and stuff like that. So it's going to be way slower. And the worst part of this is it's going to chew up a lot of stack space when you have a long string. So for each byte that you have in the string, it's going to chew up, I'm just estimating here, 8 bytes for the return address, 8 bytes for the argument, and potentially 8 bytes for the frame pointer. So we are going to chew up 24 bytes at least for each character in the string. So it's not a very good use of your stack space. But it looks fun, right? You know, it's recursive. So are we good so far with this? Yep. All right. So this means, you know, we can kind of turn everything that is a loop into recursion. So as it turns out, in terms of the theoretical side of computer science, they are equivalent concepts. Okay, if you have a programming language that has no iterations, like no while, no do loops and stuff like that, but it does support recursion, you can express the very same algorithms that you can otherwise express using a programming language that has loops, and the other way around as well. Okay. So that means if you are given a programming language that does not support recursion, but it does have loops and it has arrays, you can actually implement everything that can be done recursively as well. It's going to be uglier, but it's going to be more efficient, but they're equivalent in terms of concepts. Okay? So that brings us to the next topic here, is when should we consider recursion? Because everything can be recursive, and everything can be non-recursive. So the question is, when do we want to consider recursion as a way to implement an algorithm? So the idea is, if a problem can be, if the solution of a problem can be expressed as breaking the bigger problem into smaller problems, but each sub-problem has the same nature as the bigger problem, then it is going to be make sense. It's going to make sense to turn it into a recursive algorithm. Then the only concern is efficiency. Okay, is it really inefficient to implement it recursively, or is it kind of like it's not going to be that big of a deal? Okay, because if you have a recursive implementation of an algorithm and it's really inefficient in the sense of, oh, it's going to chew up a lot of stack space or something like that, then you probably want to look into the alternative implementation and not to use the recursive implementation. So are we good so far with this? The efficiency gain can be very significant. Okay, you know, when I was doing my own dissertation, my first algorithm or my first implementation of the algorithm was recursive, and it was really slow. I mean, it took a long time to execute, and once I turned it into an iterative version, but the same algorithm, I think it was a factor of 4 or 5, you know, in terms of how fast it went. So you can be looking into a pretty high gain in that case. So any algorithm to implement a recursive definition can be done, you know, but the question is does it make sense? Like factorial. Factorial is one of the most used examples to illustrate recursion, but yet it is also one of the easiest to turn into non-recursive algorithm. And the non-recursive version is much faster than the recursive version. Okay, so it's only really just an illustration thing, but in practice, you really should not be implementing factorial recursively. We talked about this, you know, self-similar structure, which is basically saying the big problem is broken up into smaller problems, but each smaller problem has the same nature as the big problem. And in this case, you know, self-similar action, which is kind of the same thing. the kind of solution that you have to apply has a recursive nature to it. So do we have any questions up to this point? This is really just a general discussion of recursion as a whole. So are we still good? Any questions? No questions? All right. So practical issues of recursion, we talked about this already, so this is really just a quick way to summarize. Recursion is possible because most languages maintain a context or per invocation of a subroutine. Now this is something that you would not learn from cisp440 nor 360, and it's something that you will learn in cisp310, assembly language programming. So in assembly language programming, we'll be talking about how we save the return address, the frame pointer, all the arguments, and all the local variables on the stack. It's called a context, or otherwise known as a frame. And there's one frame per invocation, not one frame per function. Okay. So when you have a recursion that happens, let's say 10 times, it's 10 levels deep, you have 10 frames, even though it's only one single function. Do you guys want to see that in a debugger? Because I can make this very visual. Okay, all right. So we'll go ahead and do some implementation here. So let's see, I can put it into the temp folder, and what should we use? Factorial? Okay. Okay, so this is the factorial program, and we have unsigned factorial. And to illustrate this, I can't use the ternary operator one because otherwise I don't have a good place to put a breakpoint because it's only one line. So I have to do it in a slightly longer version. Huh? You can break per function. Then you get to the last one. Okay, it might still work. So we'll see whether the debugger can handle that. So when n does not equal to 0, which means n is greater than 0 in this case, then we want to do the recursion. So we want to return n times the factorial of n minus 1. Otherwise, we just return a 1, and that's my factorial. So now we go to main. Oops. I accidentally hit F1. Okay, so we want to compute the factorial of, let's say, 5, okay? Okay. And this is the entire program. Has no printf, has no actual output whatsoever, because everything that I'm going to do it in GDB, so there's no need for the program itself to have any type of input nor output. So gcc-g and then -o fact.c, and then we do a GDB fact like so, and then we want to put a breakpoint on the subroutine called factorial. So now we run the program. Okay, I can even list the program. This is the source code of the program. So when I run the program, since I put a breakpoint at the entry point of factorial, so that means every time we get to line 3, it's going to stop, or it's going to pause and say, okay, we have a breakpoint here. Do you want to do something? So we can kind of examine a few things and whatnot. Okay, so run. Okay, this is the first one. It's the first iteration. Is that okay, or is it too small? A little too small. Okay, we can. How's that? Much better. Okay. Okay. This is the first invocation. The first invocation is coming from main, and n equals 5. Does that make sense? Okay. So if I continue, it will go to the second invocation, where n equals 4, n equals 3, n equals 2, n equals 1, and then finally n equals to 0. So there's nothing visual about this, right? What happened to all of the other invocations? You kept saying that each one has its own place on the stack, right? So what you need to do now is to run backtrace. BT is the abbreviation of backtrace, and it's going to show you the entire depth of invocation. So we started in main on line 8, that calls factorial, and then factorial on line 3 calls factorial again, blah, 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 blah. This is the last one we are at, okay? So now the question is, how much space are we using per invocation? Can we find out, how much space we are using per invocation? Well, let me show you another thing we can do. See all of these numbers here, #0 all the way down to #6, those are frame numbers, okay? So you can actually change the context of the debugger to any frame within this range from 0 to 6. 0 is the current frame, but you can go back to an earlier frame. So you can say frame, let's say 3, okay? So now we're getting back to frame 3 when n equals to 3, okay? So now we can check out what is n. N is 3, okay? Not very surprising. But if you do have other local variables and other types of, other arguments and whatnot, you can actually print the other local variables of that particular invocation, okay? Which is very useful in debugging, okay? If you're writing any type of subroutine recursively, this can be very helpful because it allows you to examine local variables, not only of the frame that you're currently in, but also in any earlier frame that led you to the current frame, okay? But the most important part is I can print the address of n, okay? Not really particularly meaningful to us at this point. It's just some hexadecimal number, okay? So the next thing I'm going to do is to change the frame and say, okay, let's go to another frame which is only off by 1. This is frame 2. Okay, so we're getting closer to the current frame, which is frame 0. And we're going to say print n, okay, not surprisingly, it's 2. But we also we also can print what is the address of n. This is yet another hexadecimal number. Now we can compute the size of one frame, right? You just do a subtraction. So we say, let's go ahead and subtract those two numbers. And I think it would allow me to do a $2 minus $2 minus $3, $4, 2 minus $4. No, cannot be. Is it only 8? Cannot be just 8. Oh, it's 8 unsigned integer pointers. So the best way to do this is really just to kind of copy and paste the number. So we are looking at this number minus this number here. And it takes up 32 bytes. So each frame is taking up 32 bytes, which was pretty close to what I estimated earlier, right? I estimated 24 bytes. So this is actually pretty close. That's the price that you're paying with recursive algorithms, is you're chewing up stack space. Now, all that stack space is going to be reclaimed when the first level is done. When frame 5 is done, then you're reclaiming all that space. But when it's computing, you're basically using up a lot of space, and that is why it is not efficient at all. Is that okay? Is that kind of visual or not? It's not visual in the sense of pictures, but it's visual in the sense of you can actually understand the addresses of the variables. So are we good so far? How many people know that you can do this in GDB? Okay. It's actually very helpful to be able to do this, when you're debugging a program, huh?
It's in CodeBlock. CodeBlock uses GDB.
Yeah.
They do a visual thing, but the terminal at the bottom, you can type in this.
Yep. Yep. I don't use code blocks unless I have to show people how to use code blocks, because people refuse to use VI and just GDB. All right, cool. So this is just an illustration of all the calling and returning. So I'm going to skip a good portion of this because it gets really boring really fast. So the whole point is it is actually very inefficient. Okay, the recursive way to do Fibonacci and also Pascal's identity is actually very, very inefficient. We have the implementation overhead and stuff like that. So that means, the recursive approach is good in many cases, but you have to take into consideration, are we losing a lot of efficiency? Am I chewing up a lot of stack space as a result of that? So are we okay with this slide so far? Okay. Can you guys tell me since when do you feel comfortable with recursive algorithms? Is it 400 or 430? Huh? 360? Well, they started to talk about recursion in 360, but do you feel comfortable with recursion in 360 when you were taking 360?
I think 400 is really sounds good, but I do remember.
Okay. Assembly language programming actually does help the understanding of recursion as well, because you're looking at it from the lowest possible level. Now we are not quite there yet, okay? Because I can see some kind of like we are not we haven't really touched on recursion yet, because we are just getting into subroutines, with tomorrow's lecture in cisp 310. But when you're done with 310, you should have a pretty good understanding of how recursion works, because it's really just saying, oh, okay, we have to push all of the arguments, all the local variables, all the registers that we are using on the stack. Okay, so this is the last slide related to big O, big omega, and big theta. And this one does have some, let's just say, heavy-duty math in it. So we start with linear search, and we want to find out, how do we know the time complexity of linear search is big theta of n. And the notation is T of n is the time it takes for a linear search algorithm to finish the problem, and n is the size of the problem, which is the length of the array. Okay. And in this case, I think we are measuring, we are making the assumption that what you're looking for may not be in the array. So we are looking at the worst case, not the best case, because if you're looking at linear search and you say, what if what we're searching for is the first item of the array? Well, that's your best case. It's constant time. But you cannot use constant time, or the best case as your average case. So your average case is actually n divided by 2, assuming that you're only looking for things that are in the array, and you have an even probability of looking for any particular item, then the average is n divided by 2. The worst case is just n, because if the item is not in the array in linear search, you have to look through the entire thing to confirm that the thing that you're looking for is not in the array. And we are making the assumption that the array is not sorted. Because if an array is sorted, you can actually come to a conclusion earlier than having to finish the entire thing. Okay, so this is the pseudocode of linear search, and we are using a recursive version of linear search. So this is pseudocode. It's not in C. Okay, I'm using the same notation that I use in CISP 300 when I teach CISP 300. So is that okay? But do I need to kind of explain this notation, or is it kind of self-explanatory enough that you guys go like, yeah, we got it? It's kind of the same thing, except it's a lot more verbose, than C and C++. So we have the subroutine definition starting from here and is ending here. The name of the subroutine is linear search. It has a bunch of parameters. A is passed by reference. B is passed by value. V is also passed by value. B is basically saying, okay, what is the start index of the array that I'm supposed to be searching from? V is the value that I'm looking for. Okay. Local variable R is a Boolean. It's either true or false. This symbol is assignment. Okay. I really hate to use a single equal symbol to represent assignment, because a single equal symbol should mean comparison. Does the right-hand side equal to the right-hand side? Does the right-hand side equal to the left-hand side? Okay, it should not be specifying we copy something from the right hand side to the left hand side. So that's why I always tend to use an arrow to represent assignment. And this is one of the biggest problem. Well, okay, I wouldn't say biggest problem, but it's a very common problem. How many people have been burned by using a single equal symbol when you're supposed to be using double equal? Many times. And that's why I don't like it, because it doesn't make sense, okay? So this is just assignment. So R is initialized to false, which basically is making the assumption of, let's just assume the element is not in the array until we confirm that it is, okay? If B is less than bar A bar, so bar A bar is not cardinality of a set, it is the size of the array, okay? So if the index B is still less than the number of items in the array, then we still have something to search. Otherwise, we don't have anything to search, and then we get out of the conditional statement, and then we just return false in that case. So if B is in fact less than bar A bar, then we have at least one element to examine, which is A bracket B. Okay, so this invocation is only going to look at one item in the array, which is according to the index of B. If it does equal to V, then the OR is going to short circuit. So I'm still using short circuit evaluation here. So this OR is not going to evaluate the right hand side if the left hand side is true already. So does that ring a bell? Your short circuit evaluation, otherwise known as lazy evaluation? Is that okay? All right, cool. So what if A bracket B does not equal to V? Then I say, let's search again. Search in array A, but now the start index is B plus 1, the next one, okay? And we're still passing V, which is the value being searched for. So now I turn it into a recursive subroutine, okay? Sorry?
I said now it's slow and inefficient.
Well, but it's easy to analyze, okay? So the reason why this is now easy to analyze is because now you can see that the amount of time to handle the case of n is some kind of constant k1 plus the amount of time that we need to solve the case of t of n minus 1. So anything that looks like this has the time complexity, has a type bound of big theta of n. Okay? So do we have any questions about linear search? Okay, so let's move on to the next one. So we are now looking at selection sort, bubble sort, insertion sort, and etc. Because there are quite a few sorting algorithms that have the same time complexity. We're almost running out of time, so maybe I'll start on this next time, because it doesn't make sense to get started and go like, oops, we're running out of time. So we'll start on this next time, but you guys should read ahead of me a little bit. So I'll see you next Monday, which is not exam 2. Exam 2 is on Wednesday, next Wednesday. Have a nice weekend.